This is Richard Landry, and today we're going to be doing a classification study on mushroom toxicity. So first, introduction. What we wanted to do is talk about a little bit the importance of this project. So first of all, foraged mushrooms such as truffles and morels sell at really high prices, and they're considered a high commodity in fine dining restaurants. So market value usually is a constant because these are hard to find because they can't be commercially mass harvested. So what we're going to do is provide a first type of automated step to rule out the inedible species beforehand. And this is just going to be like a first step. We're going to wait for a better model, of course, because poisonous mushrooms are very dangerous to the human body. And we just want to make sure we can rule out some that are verifiably not edible. The only ones that we really care about are the edible ones. So the focus is going to be on making a good choice as to which ones should not be eaten. So there's several predictive models that we're going to be using, and we're going to use them to test whether or not they're edible or poisonous based on the species and characteristics of the mushrooms. What we're going to do with this is it's going to be a classification process, and we're only using a set amount of data, so our product won't be using streaming or time train based data. So the analytics, streaming analytics and relevant technologies are not going to be used. The classification scheme, as I said, has a fixed number of parameters, and so only needs to be run on a new specimen with previous training data. So we're only using one large collection of data in this particular project, so it's going to be split into a testing and training set as usual, and we'll only need to load that particular set into our analysis software. So, as far as data integration is concerned, we're going to be using a combination of R and Python, and this will all be done on the same notebook sort of seamlessly. I figured out a way you can do that. So that's going to be pretty easy. It'll all be contained on one notebook that you can look at or refer to now if you want. The data repository is the mushrooms database, and it was obtained through, you can see the link here, and we found it off of the Kaggle website, but I did not actually put that. But you can just find it by looking it up and going to the archive here. And we're starting by just reading the CSV data, which is common separate values, as you probably know, from the current working directory using the R programming language into a Jupyter notebook. So this is all stuff that we've learned in the course. We have, through looking at it, which we'll do in a second, we have 8,124 different samples and 22 characteristics per sample. Then there's a final characteristic which tells us whether it is edible or poisonous. So we know beforehand whether they are, and this is just a way that we can, test and train the model and stuff. Okay, so discovery and exploration. First, we explore the features using R because it's easier to do. R is chosen because the data set is not too large, so it doesn't make R. It's not very difficult for our language to take all into memory. And some of the plot routines are just far superior to others in R itself. So I'm using that because I like the graphs more. When initially working with the data, the necessary libraries and utilities can be found in the fully functional notebook, as I said before, and associated with this report, which is also listed in my GitHub. The field class is either an E or a P for poisonous value. So later on, we're going to do hot encoding to change those to ones and zeros. We're going to change all of the values through this type of encoding just to give them numerical values so we can compare them in graphs. We're also checking how many species are in each category to verify that there are enough of each to make a meaningful analysis, and we found out that there are 4,208 edible and 3,916 poisonous. So it's kind of a balanced amount of percentage edible to percentage poisonous. So, feature analysis. We're going to reframe the features by converting the factor data into numeric data, like I said. For a visualization of the features, we're going to use density plots first, just to give us an idea of what things look like, to present both the value density and the degree of separation of the two sets of values on each feature dimension. So, of course, since there's 22, we're going to have 22 different slides to look at. There's no perfect separation between any of the features, as expected, but we do have some good separations for spore print color, ring type, population, and habitat. So there's also a type correspondence to some of the values, like veil type and stalk shape. And so here are some of the graphs we see here. Particular node, you can see veil type, there's a very strong relationship between both poisonous and edible. As you can see, those are labeled here. And then we also have some interesting things to look at with odor. As you can see, there are two very strong peaks that are not well correlated. The same goes with, let's see, spore print color. There are a few of them that are just very opposite in look. And so some of those are the ones we're going to see have more of a strong relationship to tell us one is one or the other. So this is sort of the feature diagram that I referred to in most of the model, just to make sure that I was on the right track and that the model was performing nominally. So, predictive models. No, so now we're getting to the ETL sort of part. We've chosen 3 models in R and 1 more model using neural network in Python to determine the best way to train. In the R implementation, we're using a random forest model, then a gradient boosting machine model, and then finally an XGBoost model, which is almost, there's not very much of a difference between the gradient boosting and the XGBoost. I just wanted to see if maybe there was any performance gain, but the reality is, since it was such a small sample set, it didn't really matter very much. I think if this were broadened to a larger spectrum of different species and maybe different characteristics, and even put in a classification for like visual imaging, we would have a different situation. But as of right now, I just chose these 3. And then finally, the Python implementation uses a neural network with the atom optimization, and that was the only one that I used because most of them seem fairly similar. So for the decision tree analysis, this is sort of referring to the R implementations. Okay, so first we start with decision trees, and those are just a classification model which works on the concept of information gaining at every node. So for all data points, decision tree tries to classify the points of the nodes and check for information gained at each node. It then classifies at the node where the information is gained. It maximizes it, basically. So random forest is an ensemble machine learning algorithm that functions by creating multiple decision trees and then combining the output generated by each of the decision trees. So this is sort of a diagram of the random forest right here. Random forest works like decision trees, but does not select all data points and variables in the trees. It also randomly samples data points and variables in each created tree and combines the output. Then it removes the bias that a decision tree model might introduce in the system by improving the predictive power significantly. So this is the initial test of a random forest model. As you can see, we have perfection in the confusion matrix because this demonstrates all of the test samples are, when it's predicted right on the correct spot. So it predicted all of them poisonous and all of them edible for the ones that were poisonous and ones that were edible. So in our truth diagram, we see that they fall in the exact places that they should be. So the metric that we're going to use to test for this, besides just looking at the confusion matrix, is the area under the curve, and in this case, it's 100%. So we have a really good showing for the random forest model. Now, in the gradient boosting model, we built an ensemble of deep independent trees, and now the GBMs are going to build an ensemble of shallow, weak successive trees, where each tree learning and improving on the previous level of trees. So now boosting, in the name, adds the new models to an ensemble sequentially. So for each iteration, it trains the new weak base layer with respect to the error of the whole ensemble. And when it's combined, the weak successive trees produce a powerful collective. So gradient boosting is a gradient descent algorithm, which we learned in the class, that can be performed on any differentiable loss function. So anything differentiable, which implies, I guess, in a certain sense, that for the most part will be continuous. And then the process continues improving to minimize all errors. But sometimes this is overemphasize outliers, and that causes overfitting. So we're also using a little cross-validation scheme in both the XG boost and the gradient boosting model. So here's the gradient boosting model at work, and this was actually a second optimization step using the confusion matrix. And as we can see, we have two incorrect choices. So what's good about these incorrect choices and good about looking at a confusion matrix is now we can tell, okay, the one we don't want to see is this one right here. We don't want to see a true poisonous and a falsely predicted true poisonous. So it says that if the model would tell us that this were edible, that would be very dangerous for this type of model. So we do see that the errors in the model are only in the sort of non-dangerous side, because basically it's telling us, oh, some mushrooms that were in fact edible, they said it was poisonous. But that doesn't, that's not going to hurt you. That will just throw out some mushrooms that could have been edible. But that's not a bad thing, which is why a confusion matrix in this case is good for looking at a binary characteristic of edible versus poisonous. So in this case, we have an AUC of 99.9%, and it's okay because we don't have any of those false negatives. Okay, so now we're going to look at the neural network model. This is just a basic diagram of a neural network. In our case, we'll have 22 inputs here in the input layer. We're going to have a few hidden layers that we'll construct, and you'll see them in the notebook. And finally, an output layer that's going to give us a binary output. So we're just going to have edible or poisonous at the end. So we're going to be using the TensorFlow backend under the Keras framework. And Keras is a high-level neural network API written in Python. And we'll only look at the atom optimization, which is a variation on a stochastic gradient optimizing scheme. So before we were looking at gradient descent algorithms, and this one is a stochastic one, which means that it randomly shifts at each optimization step, finding a perpendicular to the hyperdimension that we're looking at. Okay, so it supports convolutional recurrent neural networks. And since we're going to use that, we're not really going to talk about it. But first we have to import the Keras library and create the neural network layers. Okay, so what we've done here is we've already used the notebook. You can follow along in the notebook if you'd like. And we've implemented the model. In our first test, we found using a batch size at around 128, which is, a power of 2 sort of factor. Epochs to 100, just because 100 seemed like a decent amount. So that's how long we've run the model, and the number of epochs, and the number of batch size just fits the amount of samples that we were working with. So it seemed to be the best out of all the tries that we used. There were 2 hidden layers in this one, and so it started at 22, and the first hidden layer was dropped down to 11 inputs, and then the second layer was dropped down to 5 inputs, and then the final one, of course, is just the binary output. In this one, the AUC was 95.3%, which is not that great. So I changed something, and I decided, well, I'll put the hidden layers both equal to the same amount as the input layer. So I changed them both to 22, and the result was a better output as before. So you can see the loss function and the training and validation accuracy at the top for the first, and then for the second one, there's a significant difference in both the loss and in the accuracy. In this case, it was AUC equals 98.1%, which is verifiably better. So in this result, we sort of found out that the random forest model was the best choice. So in our case study, there isn't really a need for security measures in this type of study because a database lookup would need a very small amount. As long as there was no way to actually modify the initial data, there wouldn't be a huge security risk in somebody looking in on this information. The main database would need only retain the original measurements, classifications, and the relevant characteristics used in the experimental model. Future design would permit updating the data set with new measurements on the specimens and determined to be either poisonous or edible. And finally, they can just be added to the overall set as needed. In conclusion, we were able to predict with very high accuracy the poisonous and edible mushrooms based on the models used. All of them were above 95%. So random forest, gradient boosting, XGBoost was included in the report, of course, you can see that. And it actually didn't do as well as the gradient boosting machine. So finally, the neural network, and we found there are ways to optimize that. But it turns out that the random forest model, the first model that I tried, was the best. So in both the boosting models, we were using cross-validation, and as I said, the best prediction was using the random forest. Thank you.